I'm going to use the takeaway model. So first, I need to show my 302. That's 100, 200, 300. So I use 3 flats, and then I'll need to use 2 cubes, 2 little cubes, 1 and 2. So it's 300, 2, 100, 200, 300, 2. And then I need to take away 178, and whatever I'm going to be taking away, I'm going to be putting them in this little part here. So by the end of this process, I need to be having 178 in this little part here. Okay, so I need to subtract 8 little cubes, but I only have 2. So what I'm going to do right now, I'm going to need some more little cubes, and I know that there are little cubes actually in the rod, but I don't have any rods. So I need to trade 1 flat with rods, and let me see how many rods I'm going to be using. Let me place some rods on this flat here. And it seems that I need another one. Okay, so let me check. So as you can see here, so I covered the area, and let me see how many rods I used. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I am trading away and trading this flat. I'm going to put it back, and right now I'm using 10 rods. So I have 2 flats right now instead of the 3 that I had before, and I'm having 10 rods. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm having 10 rods here, and in order to be sure that we're again using the 302 number, let's see if that's the case. 100, 200, 210, 220, 230, 240, 250, 260, 270, 280, 290, 300, 301, 302. So it's again 302, but I've shown it in a different way. Okay, I need to be taking away, let me remind you that I need to be taking away 8 little cubes, but I still have 2. So I need to be making some more trades, and what I'm going to do right now, I'm going to trade 1 rod with little cubes. Let's see how many cubes I'm going to get. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can verify this. I'm going to put my little cubes here. I'm going to be needing 10. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm going to get these little cubes here, and I'm going to put the rod here. I have traded. So right now what I'm having is actually I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9 rods instead of 10 that I had before, but I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little cubes. So it's 12 cubes right now. But do I still have 302? Let's see. 100, 200, 210, 220, 230, 240, 250, 260, 270, 280, 290, 291, 292, 293, 294, 195, 296, 197, 198, 299, 300, 301, 302. I still have the 302, but it's shown a different way. And let's see right now if I can take away 178. So I need to take away 8, and I have the cubes right now. 1, 2, 3, 4, 5, 6, 7, 8. So here are the 8 little cubes in my bag. And how many am I left with? With 1, 2, 3, 4. So I'm having 4 left, 4 little cubes left. And right now I need to take away 7 dots, and I'm going to put them in my bag. 1, 2, 3, 4, 5, 6, 7. So here are the 7 dots that I've placed in my little bag, and I'm left with only 2. And I need to be taking away 1 flat. Here's my flat, it goes in my bag, and I'm left with just 1 flat. And let me check. Do I have 178 in my bag? 100, 110, 120, 130, 140, 150, 160, 170, 171, 172, 173, 174, 175, 176, 177, 178, so it's 178, which goes in my bag. And what's the difference? 124. 100, 110, 120, 121, 122, 123, 124. So this is how actually the numbers match with my cubes. Thank you.
Okay, so what we have seen right now is actually the teacher doing a very careful way, a very careful matching between the representation. But the teacher was also using language very carefully, because the teacher was referring to trade. He was not referring to, let's say, breaking apart the cubes. It's also important to keep in mind that the teacher was emphasizing a very key mathematical idea, the preservation of value. Regardless of how we are representing 302, it's still 302. And we need to be emphasizing this a lot in order to help students understand. And also, in order to avoid creating these parallel words, the teacher was very careful in how he was using the representations and the symbols and the algorithm at the same time. Also notice that even when he traded the 10 rods with the flat, he shifted the flats to the left in order to make some space for the rods, and he did this on purpose because he wanted the way that the cubes are arranged on the table to match the algorithm, the way that 302 is represented. So these are important things to notice. Moving to the multiplication of multi-digit numbers, one of the challenges that we have is how we can convince our students that in the second partial product, they need to move one place to the left. For students, this seems like magic. And what we could do right now is we could use, the representation that we have right now. And we're going to be talking about 2 different algorithms, the traditional algorithm and an alternative algorithm to help our students develop understanding. So here I'm using an area model, and I have represented 32 times 15 in this way. That's 32, and that's 15. And as you can see, I'm using different colors to represent the partial products. And this is the algorithm that we can use first in order to help students understand that these different partial products actually go with the representation. So if I multiply the 5 times 2, these are the 10. And actually, I could also be using Dean's blocks, and that would be the 10 little cubes. If I multiply the 5 times 30, that's 150. And I could be representing this by using the rods. If I multiply the 10 by 2, again, that's 20. That's 2 rods. And 10 multiplied by 30, it's 300, which actually gives me the 480. And having done this, I can then move to the next representation, which is actually the more traditional algorithm. And I need to be discussing with my students what this 160 means. And I could do this by using this representation. It's this thing here, but also using the partial products from above. And when it comes to 320, I need to be discussing that actually this 32 is 320. And it could be represented by these cubes here and also these partial products here. So I need to be doing this careful work and matching in order to help my students draw connections between this standard algorithm, which is sometimes confusing for students, with the alternative algorithm and the representation. And in doing so, I am, helping my students understand that it's not mathematics. Oftentimes, we're doing these steps. We're saying, okay, move one place to the left. But why are we doing that? We need to be helping our students understand the mathematical concept. Shifting to division of whole numbers, let's assume that we are teaching 72 divided by 4, and we're going to go watch a clip from a US teacher doing this subtraction with a group of students. And notice that when the teacher starts doing that, she's going to remind students of the different meanings of division. And she's going to be using the partitive meaning of division, not the measurement one. Partitive means that I'm forming 4 groups of objects, and I have to determine how many objects I'm going to have in each group. Whereas the measurement, I know the size of the group, and I need to figure out how many groups I could make. We're going to be considering the measurement interpretation when we're going to be discussing the division of fractions. So let's watch the.
Jacob, could you put them in the middle? We're going to show our division as we go. We've been doing our division for a long time, and I don't think we're still getting the point why we're doing this subtracting.
I get a ruler.
Okay, so we have 72, right?
Yeah.
If we wanted to divide 72 by 4, what does that mean? What does that mean?
How many 4s are in 72?
It means how many 4s are in 72, but what else does it mean? Can I do it another way?
Yeah, long division.
How can I do it? But when I'm doing long division, what am I doing? I can make, what I'm finding out is 4 groups, right? All right, so let's find out 4 groups. So, let's see. The girls are 4 girls, right?
Yeah.
Jacob, you're not paying attention to me. The girls are 4 girls. So, can you divide these up among the girls, Jacob?
Yeah.
Let me see you do that without taking anything apart.
I'll try. And do what? Here.
1 for Natalie. Timmy? Can you give them each a 10? Uh-oh, can't do it, can you?
No.
All right, so how many 10s could you give them, Jacob?
1 each.
You could give them 1 each. That's why we put a 1 in the answer spot here. I can give them 1 10 each, right?
Yeah.
Okay, Jacob, how many did you give away?
4. 40.
You gave away 40. That's why we put it here. We're gonna give it away. We already know there's 110 worth, right?
Yes.
Okay. Subtract.
2. And 3.
And how many cubes do you have here?
32.
You have 3 10s and 2 1s, 32, right?
Yes.
Jose, could you pay attention for a minute?
Yeah.
Thanks. Okay, Jacob, how can you give those to the girls? How can you divide them up?
I can split them in half.
You have to take them all apart, don't you?
Yeah, but
Okay, can I see you do that? Okay, Jessica, he'll be fine. Leave him be. You still have some more, honey.
I got it. 3.
Do they all have the same amount now?
Yes.
How many do they have that are not in a tens cube?
8.
If I believe that, then I have to believe that there are 4 8s and 32.
Yep.
You believe that?
Yeah.
So we put that in our answer. So we want to know how many 4s are in 72 altogether, right?
Yeah.
Jose? We put the answer in the answer spot, up in the quotient.
Okay.
There you go. Now we want to know how many are gone. So 4 times 8 was 32, and there's none left, are there?
No.
Anybody see any left?
No.
None left. So we're all finished, aren't we?
Yeah.
That's how those cubes go with this problem.
So the teacher started by actually emphasizing that she's going, at least implicitly, that she's going to use the partitive interpretation where the 4 actually means we're forming 4 groups. And the other thing that is important to note is that she was using appropriate language. She was referring to how many tens, how many that are not in a tens cubes. She was referring to quotient. And also, a very interesting point to notice is that she was recording the steps while using the unifix cubes. This is how she tried to help students match the symbols with the representation. And actually, the other thing that she was doing, she was clarifying what each number or each step in this algorithm corresponds to. So that's an example of the long division, which oftentimes is hard for our students to understand, and how representations can help us. Now, shifting to multiplication with fractions. Again, here we need to be talking about the mathematical notion. So when I'm multiplying fractions, I'm taking a part of another part. So if it's 2/3 of 1/4, that's going to mean 2/3 multiplied by 1/4 means that I'm taking 2/3 of 1/4. And I need to be using the representation to help my students understand it. Oftentimes, we get pre-partitioned representations in the textbook. And the only thing that we're asking students to do is to simply color the representations. That's not helpful. Let's consider an alternative. So that's my unit, and I'm going to take 1/4. So I'm partitioning this in 4 equal parts, and I'm taking 1 out of this 4. That's 1/4. And right now I need to be taking 2/3 of this 1/4. So I need to be splitting my representation, this 1/4 into 3 equal parts, and I need to be taking 2 out of these 3. And the question right now is, what fractions do these orange pieces represent? And in order to answer this, I need to engage in a discussion with my students that I need to extend the lines, and I'm getting 12s, and it's 2 12s. So notice that, again, I started with the meaning of fraction multiplication, taking a part of another part. And I did not use a pre-partition representation, because a pre-partition representation is doing the thinking for the students, is actually stealing all these rich discussions that I could have with my students. I need to be showing the 1/4, I need to be showing the 2/3, and then I need to be partitioning the representation. And you could find, this way of illustrating the multiplication of fractions in this online source here. Very quickly shifting to division of fractions. That's another hard concept that we have to teach. And when I'm teaching 3 divided by 2/3, I'm going to be using the measurement interpretation. So I need to be talking about how many times can I fit 2/3 into a 3. And of course, we all know, the traditional algorithm in which we invert the second fraction and multiply. But why do we do this? And what does these 3 halves mean? So I could use representations to actually help my students understand this. And when I'm doing this, I need to be really careful, because I need to be drawing my students' attention to the fact that I'm going to be using 2 different units, the whole and a reference unit. So that's my 3. This is, how I'm starting with. And right now I need to figure out how many 2/3 I can fit into 3. So let's take 2/3. 2/3 means that I need to be dividing my whole into 3 equal parts, and I need to be taking 1 2/3. So that's my 2/3 piece. And I need to figure out how many times I can fit this 2/3 into my 1. I can fit it 1 time, and then, and here, here it can be tricky, because I need to be drawing my students' attention to the fact that this is a different unit. So I need another piece of this size. And what's the fraction of this piece? It's 1/2 actually of this 2/3. So if I'm going to use this 1/2, I covered 1 of my units. So I need to be using 1 and 1/2, or in other terms, 3 halves for each unit. So here is the 3 halves, and I need to be doing this 3 times because I have 3 units. Of course, I just move really quickly because of the interest of time, but it's conceivable that when we're working with our students, these different steps are going to be done in a much slower pace. Here is a 3, and when I have to talk about 4.5, I could connect this 4.5 to the fact that I use 1 2/3, 2 2/3, 3 2/3, and then a 4th one, and then a half of it, 4 and 1/2. Again, in doing that, I started by emphasizing the mathematics, the mathematical ideas, and then I was very careful about the different units that I was using, and I was trying to give meaning to the different numbers that are involved in an algorithm that, in essence, it could be really mathematics to students unless we help them understand. Moving to the second to last, let's assume that we're subtracting -3 from 5, and I'm going to use the color chips. And I need to be discussing with my kids that I'm using these pairs of different color chips, and when I use them, I get 0. Actually, that's the additive inverse property, and I need to be discussing this with kids. Although we can see 2 chips right now, their value is 0. So in order to do this subtraction, I'm going to start with 5, and I need to subtract 3. Actually, I need to subtract 3 negatives, 3 reds, and I don't have any red. So what should I be doing? So let's add another pair. If we add another pair, we know that this is 0. So I started with 5 plus another pair, which is 0, that's still 5. Plus another pair, which is 0, that's still 5. plus another pair which is 0, that's still 5. And I know that you are listening to me repeating this 3 times, but that's important for kids because I then need to discuss with them that I have 11 actually chips on my table, but their value is 5. I need to be doing these discussions with them. And then when I remove the 3 reds, the 3 negatives, I'm left with 8. Again, I started by clarifying what the blue and the red chips represent. I emphasize the additive inverse property, and I emphasize the preservation of the value of the mean. Okay, and let's conclude. That's the last example that I'm going to provide. And let's conclude with an example of solving a problem. That's the very well known, the pool border problem. I have a rectangular pool, and it is to be surrounded by ceramic tiles, and I want my students to figure out how many tiles I'll need for pools of various lengths and widths. I'm giving students the opportunity to figure out different ways of solving this problem, and then I present their different ways and I try to very carefully connect them to the representation. So let's assume that a group of students came up with this formula: 2 lengths plus 2 widths plus 4. I need to be shown this. That's the 2 lengths plus the 2 widths plus the 4 tiles in the corners. Let's assume that another group came up with this approach: 2 times parentheses length plus 2 plus 2 width. That's the length plus 2, and I'm taking this 2 times plus the width. Or a group might come up with the opposite, that I'm multiplying the width in this way. Again, I need to be showing this. And finally, another group might come up with this approach. I need to be showing that this represents taking the entire rectangle and then subtracting the pool. So in this way, I can help my students understand that representations can actually help us illustrate the different ways in which we can be solving this problem. And we could be talking for hours and hours, and I'm cognizant that I have taken some more time, and I apologize for that. But let me conclude by pointing your attention to some of very useful websites that you can use, where you can find online representations. Some are for free, and you can see some of these ideas and many more of what I have discussed today. With that said, a thank you to all of you, and a special thanks to the JP Das Center for the invitation. It was really a pleasure talking to you. Thank you.
Dr. Charalambous, thank you very much for your presentation.